Prior to rendering, your scene is just a collection of geometry and texture data. During rendering, that data is manipulated based on lighting algorithms in order to get the final image you see in your app. Unity has two main rendering paths, forward and deferred, each using unique techniques to obtain the final image. Deferred rendering first collects the geometric data, then applies lighting and shadows on a per pixel basis. Because of this, its performance cost is based on the area of the light applied rather than the complexity of the geometry lit. A large advantage of this is that you can have many small lights in your scene without a significant performance hit. Additionally, those lights can all be per pixel lights and have accurate, high-quality shading. Per pixel lights calculate the lighting information for each pixel, allowing detail like normal mapping, bump mapping, specularity, and shadow volumes. In contrast, vertex lights calculate the lighting at each vertex and interpolate the remaining pixels, resulting in less lighting accuracy and quality. So, deferred lighting is a good choice for if you want the highest quality lighting and a large number of lights. However, it has some notable downsides, especially for VR. First, it doesn't support multi-sample anti-aliasing, also known as MSAA, a technique used to reduce shimmering in artifacts, aliasing, at the edges of geometry. MSAA is extremely important for VR and will be talked about in more detail later. Deferred also can't render semi-transparent objects, meaning any such objects in your scene will automatically use forward rendering, but only for those objects. Lastly, it has a high upfront performance cost, making forward rendering more efficient for scenes without complex lighting. In contrast to deferred rendering, which collects geometric data in one pass, then applies lighting in a second pass, forward rendering has a base pass, which applies the lighting data for one per pixel directional light, as well as all the data for non-per pixel lights, like vertex lights and spherical harmonics. Each additional per pixel light requires another pass, meaning the lighting data for all geometry affected must be recomputed. This makes the performance cost dependent on the complexity of the scene rather than the area of the screen space receiving light. On the downside, this means forward rendering is not as scalable as deferred. Additional lights linearly increase the cost of performance. Since you're getting fewer per pixel lights, this tends to mean an increase in reliance on vertex lights, which comes with a decrease in shading quality. Also, by default, shadows are only applied in the first pass, limiting your shadow complexity to one directional light, although this can be overridden if you have the processing budget. Despite these downsides, forward rendering has some big advantages. MSAA is fully compatible at the click of a button, allowing you to smooth over aliasing caused by head motion, which looks horrible in VR. Additionally, the smaller upfront cost of forward rendering allows it to be moderately more performant than deferred rendering when used correctly. And of course, forward rendering works for semi-transparent objects. So, which is better for VR? Due to the negative effects of aliasing and the ease of implementing MSAA, forward rendering is strongly recommended for VR by both Valve and Oculus. If you're adamant about a large number of high-quality real-time lights, deferred rendering may make more sense for your project. But be warned, the increase in perceived lighting quality might be offset by aliasing.